So, good evening, all. So, myself, Harish, we are here for week uh, 12 live interaction session, which is the last regular live interaction session. We will have one more 1 hour session, that is an extra session, to be scheduled tomorrow from 6 to 7 in the evening. So, yeah, let me just share my screen. I hope it's visible now. So, so, so is my screen visible, Vivek? Because it's showing your screen is loading. Okay, now I guess it should be visible. So we are here for the week 12 live interaction session. Today is 16. So we have discussed assignment number 9 in the last session. So today we will discuss week 10 lecture notes and assignment. Okay, so in this week, uh, the brief idea was to introduce the concept of bimodules and then to relate the tensor products with it, and then define the notion of what is called extension of scalars and restriction of scalars. And then finally, we did something related to some problems related to vector spaces. So we will go one by one. I will just tell you some definitions and the facts, which you can say a short summary kind of thing for the entire week, and then we will solve the assignment number 10. Okay. So let's start with the definition of what is called a tensor product. So we have seen already tensor product and modules. So in
Sir,
this,
extra.
yes,
Hello.
Vivek. Yes, Vivek.
Sir, extra session will be in tomorrow.
Will be tomorrow from 6 to 7.
Okay, sir.
Okay. So uh, lecture 1 was about tensor factor, tensor functor. So we know what is a tensor product and we know what is a functor. So let's see what is a tensor functor. So there was a proposition which was discussed in this lecture, which is very crucial. So it says given uh, R linear maps. So here let R be a ring. So R linear map I will describe again, although I No, we have already seen the definition of it. There are two R linear map from modules M dash, M to M dash, and N to N dash. Okay, so here uh, M and N are left modules. Okay, and this is a right R module, and N dash is a left R module. So here M dash is a right R module, and M, not just M, I will say M and M dash are right R modules. Okay, and N and dash are left R modules. Okay, we have seen the definition of left and right R modules, and by R linear map, we mean a map F from M to M dash satisfying F of MR equal to FMR. So, and second is F of M1 plus M2 is F of M1 plus F of M2, and this is for all M, M1, M2 belongs to M, and R belongs to R. So it's a homomorphism simply, and it is compatible with the additive operation of the abelian group structure inside the module, and it's when M is M times R, or when its image under F is just Fm times R. Okay, so it's linear in with respect to the ring as well. So that's why it's called R linear map. Similarly, you have G from N to N dash. Okay, so there are given two R linear maps, F from M to M dash and G from M to N to N dash. Then this proposition says that there exists a unique Z linear map. So here the ring is Z. For any arbitrary ring R, it was there. So there exists Z linear map T from the tensor product of N, M and N to the tensor product of M and N dash, satisfying T of M tensor N is equal to Fm tensor Gn. So given a M inside M, Fm will lie in M dash, and given a N inside capital N, Gn will lie inside N dash. So it's saying कि given two R linear maps from M to M dash and N to N dash, you can get a Z linear map from M tensor N to M dash tensor N dash, and which is unique in the sense that it is expressible in terms of F and G. So just taking the image of M under F tensor with image of N under G. So this is for all M belongs to N and M belongs to N. Given that it is a Z linear map, this Z linearity comes into the picture, and it implies T of summation of I equal to 1 to K Mi tensor with Ni is nothing but summation. So you can take this summation out because it's Z linear. So it is linear. It is compatible with the addition. This is K F M I tensor. So this is something. Now we comes to the categorical part of this topic. So says let this C be a category with objects being the pairs. What kind of pairs will be there? The pairs of the form Mn such that M is a right R module. So this is C of R, let's say. R is a for a given ring R. For a given ring R, we can define a category C of R. Okay. So such that the objects are the tuples M comma N, where M is any right R module and N is a left R module. So it is a collection of all tuples. One is a right module and another is a left module with respect to the ring R. And now we have defined the objects and arrows are from M to N. You have an arrow M dash N dash. So this is a pair, this is a pair. So you have an arrow from M comma N to M dash comma N dash. Uh, just a second. This- The pair F comma G, where F from M to M dash and G from N to N dash is R linear. So you have the objects to be the tuples and arrows are uh, from M comma N to N dash comma N dash. The arrows are of the form F comma G, where F is a map from M to M dash and N is a R linear map from N to N dash. Okay. So it's a tuple consisting of two R linear maps. One is from M to M dash and another is from M to M dash. So this forms a category. It's a exercise. Check that CR is a category. And here we will define a functor. Define a functor tensor of R in the following way. Okay. So this is C tensor R, C from C R. Okay, the category CR we have seen, and then any Z modules, Z mod This is the category of Z modules. From the category of uh, pairs, right modules and left arm modules, we can define a pointer to Z module in the following sense: M tuple M comma N will be mapped to tensor product of M and N over R. So it's a Z module. One can see that, and it is it has some arrow F to G, F comma G from Mn to M dash N dash. Then that arrow is mapped to the arrow F tensor G, which is nothing but sending an element M tensor N to M tensor N dash. So in this way, this also defines a functor. So exercise is again check that tensor R is a functor. Okay, that was something which was discussed in lecture 1. Then the main thing starts from lecture 2 onwards, that is the bimodules tensor. So lecture 2 and 3 I will just combinedly explain. First is the definition of bimodules. So you know what is a module. So it's just a abelian group over a ring which satisfies all properties similar to the vector space. Okay, if your ring underlined is a ring is a field, then we say that it's a vector space. If it's an arbitrary ring, then we say it's a uh, module. And left and right module means module means the multiplication of, from the ring is from the left side, and multiplication with the elements of the ring is from the right side. Then it will be termed as the right module. So just uh, through which side you are multiplying the elements of the ring are. Accordingly, you will say whether it's a left ring or whether it's a left arm module or right arm module. Okay. Now, by modules, what it does, combine both these concepts. So let R S be rings. Okay, so there are two rings R and S. Then you say something is an RS bimodule. When RS bimodule K is an abelian group K plus with a left R module structure. So it's an abelian group K which is having a left R module structure and a right S module structure. So it is having both right and left module structure, but left R module structure is from R and right module structure is with respect to the ring S. Okay, right S module structure such that R X S is equal to, so you have X, you are multiplying from left side the element of R, and whatever resultant you are getting, you are multiplying it with the uh, from left, sorry, right, it from the element of S, and that is same as R X S. That is, you first multiply from right the element, and then you multiply with the element of the ring R. Okay, so that is for all X is small here. X is supposed to be small. For all X belongs to X, R belongs to R, and S belongs to. Okay. This is sorry, not X. This is K. Okay. So you have both the module structures, the left and right module structure. And that's why it's called a bimodule. Examples: you can take R to be a ring. R is always a ring, so it is not no need to mention it. You can simply say that R is a RR bimodule. So you have the left multiplication, left module structure with respect to R, and you have the left multiplication module structure with respect to sorry, with the right module structure also with respect to R, and that's why any ring R is a RR module. So left module structure you can simply give like that. It's very trivial. So on R is given S. So R dot S is simply R S. Okay. For all R belongs to R and S belongs to, and similarly the right R module is nothing again. You just take the multiplication inside the ring. Okay. Here this is also R, na? Underline set is also R, and the scalar multiplication is also coming from the R. Let's say I will say it R just to look give notation. Let's say S is coming from the set, R is the scalar, then you just define it as SR, or again R belongs to R and S belongs to R. So it's simply just the multiplication you need to take, and so you can give a right and left R modular structure over the ring itself, because the multiplication is there inside the ring, and it is compatible with the addition and the scalar multiplication operation, because you have seen that the distributive property of the ring will help us make it a module. So it's a RR bimodule. Okay. The second interesting example is M, the left arm module. So let M be a left arm module, then any left arm module is always a RZ bimodule. So as per the definition, there should be a left and right uh, module structure. So M is a left arm module, so R, left module structure is coming from the R, and the right module structure must be coming from the Z. We will see that how it will come. So this is via R dot X is simply just to take R dot X from the R module structure of structure on M. So left R module structure on M. And X dot N is just to have X plus X plus dot plus X. This is N many times for N greater than 0 and minus of X plus this if n is less than 0 and this is 0 then equal to 0. So you have this is for all n belongs to z and x belongs to r, and this was for okay. So see, n is coming from an integer, so x dot n is just to add x n many times in the module m. It is possible because m is a abelian group with respect to addition, and if n is negative, then you add it n many minus of n many times, that is some positive number, and then you take the minus of it. Okay, and if n is 0, then you simply get 0. So this way you can define the right module structure over it, and thus it becomes a bimodule. Okay. Third example is if n is a right R module, then n is a ZR bimodule. Same, you have R module structure from right. So here also the R module structure will come from right, and Z will give you the left R module, left module structure. So it will be a ZR module. Earlier we have RZ module because R was giving the module structure from left. Here the R will be giving the module structure from right. So it will be a ZR bimodule. Now the interesting part comes, that is bimodules and tensor products. Bimodules and tensor products. So now what is this? So for that you have a proposition which says let R comma S comma T be rings, and suppose M is a SR Y module, and N is a, so you have three rings R, S, T. M is a SR bimodule. It is having the left module structure from S, and it is having the right module structure from R. So then, and N is another bimodule which is having RT bimodule structure, the left bimodule structure from R, and the right the left module structure from R, and the right module structure from T, then the tensor M tensor R N becomes a ST uh, bimodule. Okay, so how it is happening? So see, you have M tensor R N. So M is having uh, SR bimodule structure, and N is having R T bimodule structure. Then what we get, so this R and R you can say will be absorbed, and we will be having, oh, this is not visible. Maybe this color I can use. This will give you ST bimodule structure on M tensor, and is given by is given via. Okay, so uh, how the module structure is coming? So you are having an element small s, and the arbitrary element in M tensor n is of the form summation I equal to 1 to k mi tensor ni, and then see M is a left s module, right? Because it has a SR bimodule structure. You can use the left module structure over M coming from S and just define it as summation of S mi tensor ni I equal to 1 to k, and this is happening for all mi belongs to M, ni belongs to N, and all S belongs to S, and T belongs to. Okay, so and summation of k equal to, sorry, I equal to 1 to k. So this is the left module structure coming from the S. For making it an ST bimodule, we must need a right module structure coming from the T. So we have summation I equal to 1 to k mi tensor ni dot T is equal to summation I equal to 1 to k mi tensor nit. This is for all mi belongs to M, ni belongs to N, and T belongs to T. Okay. Here we don't need this T belongs to T. Yeah. So this is the module structure, and what is important here is to understand the proof of it, but I don't think that we had that much of time to discuss the proof also. If time permits, then we will see. Otherwise, it's good to move to the next uh, concept. I wanted to discuss this because this is a nice theory was coming up, but we are not having that much time. So we, we will skip this for the moment. Okay. We will directly come to lecture 4, which says answer product of modules over commutative. So till now we were not assuming the ring to be commutative or non-commutative. We were just doing it for any arbitrary rings. But what if we have a commutative ring and then we see the tensor product of modules over that commutative ring? Then what happens? So let R be a commutative ring M and B R modules. So since it is a commutative ring, so they are left module as well as the right module because it will commute, right? So it has no meaning of saying a left module or a right module because R is a commutative ring. So then M comma N R. So if it is a left module and a right module both, then this M and N are both R are bimodules, right? Because they have the module structure with respect to the R from the left side and from the right side as well. So this is via we have R dot X is simply R dot X. Let's say these are left R modules, and this is given, and for N we have S dot X. It's just again S dot X. This is also given, and this should hold for all R in your for all R belongs to R, S belongs to S, X belongs to M. Okay. So yeah. So left structure is given similarly. R dot X is R dot X because it's the left of structure is coming by the given hypothesis, and then how you one can define the right structure. So X dot S, simply define it to be S dot X from the left side. So what will happen? See, for a right module, you need X dot S dot R to be X dot S, and then sorry, to be X dot SR. So you need commutativity to ensure this property. But if you have this, so you have X dot S to be what? S dot X, and then again from the right we are applying R, so it will be RS dot X, and this thing is by definition SR dot X. So they need not be same if your ring is not commutative. But if the ring is commutative, then RS is same as SR. This property will hold, and thus it will become a right arm motif. To ensure this property, we need the commutativity of the ring. Okay.
Sir,
Yes.
sir, Rx is equal to Rx. That is given. That
So
means
this is the left module structure. Na? The R is multiplying from left. So we have already assumed that M and N are left R modules. So left multiplication is already given to us. And the right multiplication we are defining using the commutativity to be just the left multiplication. Okay.
Yes. Okay. X. In the
X dot
second part,
S, X
X
dot
dot
S
S.
is simply so you want to see what is X after multiplying with the scalar S. So we will say that it is just S dot X. So S dot X you have because of the left module structure given to you, and we define the right module structure to be same as this. But it must, all the properties we will see considering it is a right module. So that's why I'm saying that X, we have to check that X dot S dot R is same as X dot SR. This is what we need to check to make as a property of right module. So we check that it is coming RS dot X and here it is SR dot X. So these both are same. If and only if RS equal to SR, that means for all S and R, that means your ring is commutative. Okay.
Okay.
So here's this rough part. Okay. So this is for R belongs to R, S belongs to S, and X belongs to. Similarly, you can define the R module, RR module structure on N. So I'm writing for all X belongs to M or X belongs to N. Similarly, right? There is nothing extra to be done. So now what is crucial is you have the RR module structure over M and R, then your look at this tensor product M tensor R over N. So this is having, this is RR mod by module, this thing, and this is also RR by module. So this R and this R will be absorbed, right? And we will have just this and this. So M cross N, M tensor N is a RR by module. And something is a RR by module, you can simply say that it's a left and right R module. Okay. Now this implies M tensor R has left R module structure and right R module structure. Also, since R is commutative, so the left and R module structure coincide. So R is commutative, left and right R module structure coincide. Okay, and thus M tensor N is a, you can simply say that it's a R module. So now this has something uh, interesting again, that it satisfies a universal property, a special kind of universal property. This has another uh, type of universal equal property, which we will see. That is position, let m, n, and k be R modules, R being a commutative ring, and let f from m cross n k be R linear, R bilinear. Bilinear means it is linear in each coordinate. That is, say what is bilinear means. You have first f of m1 plus m2 comma n is f of m1 comma n plus f of m2 comma n, and the second thing is f of m m1 plus m2 is f of m comma n1 plus f of m comma n2, and that is for all m m1 m2 belongs to m, and for all n m1 and n2 belongs to n. And the third thing is the linear, the scalar multiplication part. F of Rm comma n is R dot f of m comma n, and that is same as f of m comma Rm. Okay. This is also for all R belongs to. Okay. So if you have a bilinear map from m cross n to k, then there exists unique R linear map f delta from m tensor R n k, such that f, so uh, does that f compose alpha is equal to f. Okay. So what's the situation? You have from m cross n to k bilinear map f or bilinear map m cross n to m tensor n. We have a map alpha. We know that what this map does, maps the tuple m comma n to m tensor n. Okay, and then this induces a map f tilde, which is R linear. Okay, this is R bilinear. Writing here, I have already written. So this is what is happening. Okay, and so this diagram is commutative. So this is universal property for tensor products. Now, lecture 5, something extension of scalars was discussed. We will see that also, and then we will come to problems. So before defining extension of scalars, uh, let's understand what is called a restriction of scalars. Restriction of scalars, and what it is. This is this says let R comma S be rings and R to S phi be a ring homomorphism that any S module N acquires an R module structure via uh, R dot N. So R and S are two rings, and from R to S you have a ring homomorphism. So uh, uh, any module N that is having an S module structure, you can give it an R module structure using this homomorphism. How? So R module structure is given that R dot N is nothing but phi R dot N. So this phi R belongs to S, and this is from the S module structure. So using the S module structure on N, one can define the R module structure over. Okay. Yeah. So that is the restriction of scalars. Why it is called the restriction of scalars? Because uh, if R is a subset of S, then you can simply take phi to be the inclusion map, right? So you have a module structure over the bigger set, the the module structure coming from the bigger set S, and then you define a module structure for the smaller set, that is R. That is why it's called a restriction of scalars, because you can restrict your scalars to a subset of S using this this natural idea. So the push example is, as I said, if so you take a ring that is a subring of another ring, and you have the net inclusion map. Okay, the inclusion map. Then uh, you can say that any complex or any module over the ring, complex ring. So complex ring is a field. So module becomes a vector space. So any C vector space. R is also a field. So here also the module is set with a vector space, can be viewed as a R vector space, which is true, right? Okay. So from here, it comes to the natural question comes that what about extension of scalars? So by extension of scalars, I mean that R to S be a ring homomorphism. So and let M be a left R module. Then using the module structure over uh, M, can we construct a S module from it? So that is the question, and that question is precisely the answer of this question is precisely what is called the extension of scalars. Okay, so you are extending now scalar to the S. So how we can do that? So see, before that we will see a few things. So clearly, as we saw earlier, S is a SS bimodule because S is a ring. It has a left module structure from S and it has a right module structure from S. So by restriction of scalars, we may give a we can give S the structure of give S a structure of RS bimodule. So it is a S2 it is a SS bimodule. Now we are restricting the scalars from one side and making it a RS bimodule. This will be via R dot X is equal to just phi R dot X. The restriction part as we see earlier, and then X dot S. The right is just right part we will keep as it is, the S module, okay? Only we are restricting it from the left. Okay, this is for all X. Yes. Then parallelly, S is a SR bimodule. Now you restrict it from the other side and keep, so this part to keep as it is and restrict it in the second, the right side. So it becomes a SR bimodule, right? Parallelly. And thus, if you restrict it from both sides, then it will become a RR bimodule. Okay. So you can, given an SN bimodule, if you have a morphism from R to S, you can give an RS bimodule structure over it and the SR bimodule structure over it and an RR bimodule structure. over it. Okay, so then using this, you can simply define uh, that this f of m, I will say, this is defined as S tensor M over R. Okay, and this is SR bimodule. This is RZ bimodule. Because M is an R module, you can give an RZ bimodule structure over it. So it becomes a SZ bimodule, and thus uh, any HZ bimodule is a thus a S bimodule. Sorry, thus a S module. So see, if the ring is commutative, then we can simply say, okay, M is having a S module structure, S is having an S module structure, so they will have an S comma S module structure, and then simply, uh, sorry, here M is actually a R module, not an S module. If it would be an S module, then the thing would be easy. So what we have done, we have from the left R module structure over M, we have constructed the module S tensor M, which is having a S module structure. So this is the extension of scalars, because uh, again the same thing. In particular, you can consider phi to be a inclusion map and R to be a subset of S. So given a module structure by R, a subset of S, you can get a module structure of on S tensor M given by S. That's why it's called the extension of scalars. Now this is some things still one should know. I will just write. So say Fm S tensor M is obtained by extension of scalars from M. And how it is obtained? So you have S multiplied with an arbitrary element of S tensor M, that is Si tensor Mi, I equal to K, and Si to S, and then Mi is from M. So you how this multiplication uh, given by S dot this is the is equal to, so I should have write it here. This is you multiply S to the left side of this, that is S Si tensor Mi. So this is an element of S, this is an element of S. So the SSI will be an element of S, and Mi is a anywhere element of M. So this will belong to S tensor Mi, and the linear sum will again belong to S tensor Mi. So SSI belongs to S, and Mi belongs to. So this is how the extension of scalars is coming into the picture. So the properties, some properties we will see. First one is from M to S tensor R M. M is a R module, and this is an S module. You have a map phi such that M is mapped to one tensor M is an R linear map. So if you map M to M tensor one tensor M, then this map is a linear map with respect to R. Second thing is let N be any S module and let F from M to N be R linear, which is R module. Then there exists a unique F tilde as said S tensor R to M is a map from S tensor R to M. Uh, sorry, it is a map from S tensor M to N such that one the first is F tilde is S linear, second is F compose F delta composed with psi is equal to F. So now try to understand what is happening. So you have a map from M to N, that is F, and from M to S tensor F tensor Rm, you have the simply the uh, xi map, the above xi map, right? This, then it induces a map from S tensor M to F, which is nothing but F tilde, and this is also a linear map. Okay. Okay. Then finally, in the problem session, uh, tensor product of vector spaces was discussed. I will just define the definition and the results I will just write, and then we can move to the assignment problems. Tensor product of vector spaces. It says let F be a field V comma W are vector spaces over F, and given any uh, for given any F bilinear maps V cross W to Z, there is a bilinear map F. V cross W Z. There exists a unique, unique we can say, but there exists some F tilde from V tensor W to Z such that again you can have the universal property kind of thing. From V cross W to Z, you have F. From V tensor W, from V cross W to uh, V tensor W, you have the map alpha, the usual map, and from V cross W to Z, it induces F delta, which is linear. Okay, so this is linear, F linear. There are just a F linear map F delta from V cross W to Z, such that this commutes. So you have this commutes. So you have F delta composed with alpha is nothing but F. So then what is, so this is how the tensor product is defined. So it's just a tensor product of modules, and you instead of rings you get the field. There you also have a universal property. So this is just the universal property for vector spaces. Just the modules. As a modules, you have a vector, universal property. It's the same universal property, but the underlying objects are now uh, vector spaces. And vector spaces is actually are modules, but instead of rings, we are having restricting it to the fields. Okay, so it's a special case of tensor product of modules. So it has first some properties. F tensor F over F is F if dimension of V is equal to N, dimension of W is equal to M, then dimension of V tensor W over F is M. Okay, so we have dimension of V to Vn, dimension W to Vm, then the tensor product will have the dimension M. Third property is so the V star, that is a set vector spaces of all vector space of all linear functions from V to F. V star tensor with W is isomorphic to the vector space of uh, all linear transformations from V to W. So this is what I think should be enough to start the uh, discussion. I just leave something in the bimodules and tensor product part. So that was some proof part, and which is giving some construction, but I don't think that that is immediately needed for solving the question. So we will move to the assignment solution. Okay, and let me just copy paste the first question. So So it says choose all correct options. First one is dimension of Rn tensor Rn is m plus n. Dimension of Rn tensor Rm is mn. 2 by 3 tensor 3 equal to 1. Uh, uh, Tensor 2 in R tensor R over Q, and A tensor B equal to 1. Tensor AB in R tensor R over Q. So yes, any guesses? This one is easy, right? We have just seen.
Yes, sir. Second is correct. Option
Second
number
is
B, I think.
option number B is correct because dimension of
E cross W
yes
property.
B tensor F W is dimension of V times dimension of W. Okay, so this is the part. Yeah. Now what about C? What about C?
Mm,
2 by 3 tensor 3. So this is inside Q, right? And the tensor product is also in Q, right? So we can move this to the other side. You can write it as 1 dot 2 tensor 3, and that is 1 tensor 2 3 dot 3. This is since 2 by 3 is inside Q, and we are considering the tensor product over Q. So 3 to 3 will cancel out, and this will be 1 tensor 2. Okay. But what about the next part? So here you can't do that because here it is saying for any AB belongs to R. If you take
okay.
A and B belongs to some Q rational,
Rational. If
irrational,
yes.
then it will be a problem. Let's say A is E exponential and B is pi. Then E tensor pi is not equal to 1 tensor AB because E and A, sorry, E and pi belongs to irrational. Here AB, in place of AB, I should write E pi. So in general, it might not be true, but you can only move the elements of the underlying ring. Here, the underlying ring is a field that is Q, so you can move. So yeah, so B and C is correct, and D is not correct because these elements are from irrationals. Okay. So let me now see. Copy paste the next question now. So let V be a vector space over Q and W be a vector space over R. Choose all the correct answers. V tensor uh, R is a R module and it is over Q. So how can you give a R module structure? It is easy to see.
Sir, option C is right according to the last property, I think. First.
It's not exactly uh, what was there in the last property. The last property it was V star tensor W is isomorphic to home of VW. Here it is, both side home is there, but we will use that property to show that. That's okay. So A part, we have to give a R modular structure over V tensor R. So how we can do that? So let R dot V, V is an element of this capital V tensor Q. Sorry, an element we don't write the few element of R again, say maybe R dash. You just give the define it to be V tensor R dash. Okay. So this is for all R dash belongs to R, and here R is here, and V belongs to V. So then this gives a R module structure over uh, V tensor Q. You can check that it will satisfy the properties of all all properties of the module structure. Now B and C we can check it in one go. So D also is not correct. That I leave it to you. If it would be V tensor Q, then it would be V. But here instead of the Q, it is R. Okay. V tensor Q is isomorphic to V, but V tensor Q R is not isomorphic to V. This is also not correct. Okay, that is already seen because here the ring is changed, so we cannot say that it will be V only. It may or may not be. Some examples. We can see some examples for that also. So for B and C, what you do, define let phi, I will say define phi map from home R B tensor Q R comma W to home Q B comma W as so phi of F under phi will be mapped to phi of F such that so so you have a F which is a linear map from V tensor R to W, and you want to define a linear map from V to W. So how you can do that? You simply restrict it as a linear map from V to W. Okay, so phi is just a two linear map from W you can take. So See, this is you are considering as R linear map from V tensor R to W, and then it's just a restriction of it. Instead of V tensor R, we are taking from V to W. So V is already sitting here because each element of V is sitting here as uh, small v tensor 1, right? So, and uh, here the linearity is over the larger field, that is R, and here the linearity is over the smaller field, that is Q. So it is just a restriction. We just need to check the linearity over a smaller field, and all elements of these are already sitting here. So it would be just a restriction of this linearity of this map to uh, uh, home as an element of home Q V comma W. So that is one side is easy to see. Second side, what we will do, and that phi prime from home Q V comma W to home R V tensor Q. Oh, here it should be R over Q. Now we are trying to define the inverse of this map. How we will define it? So G will be mapped to phi prime of G, which is nothing but small g tensor with identity over R. Okay, so G is a linear map from V to W, and then you are sending it to an element G tensor identity of R. So G will be sending the elements of V to W. So how it will like act? So Z tensor identity of R will be mapping an element, say small v tensor R to just GV tensor of identity of R, right? And then GV is coming from the map V to W, right? So it's well defined. It's inside V, it's inside W already. And then the tensor of identity of R is just R. So, oh, sorry, it will be just GV times identity of R. So it will be just GB times R. And your W was already a vector space over R, right? So it doesn't matter. If you want, then you can actually define it in the opposite direction. Actually, you should define it like that only. So it's just identity of R times G, right? So identity of R will map it to R dot GV, and this is inside W, and this is inside R. This R dot GR is well defined, and that will lie inside W because W is a R vector space, right? So yeah, so this is how you define the map in the other side, and then the only thing to check is that I leave to you. Phi and phi prime are both linear and not just linear; they are inverse of each other, and thus you have the isomorphism. Okay. So in fact, we didn't need that home Q V comma W is isomorphic uh, V dash tensor W, V star tensor W. We didn't need that. So without that we can do. Okay. So the second part I leave it to you. Third part is maybe I will copy the question. Next question now. So it says let the the map F from C n to C such that if P is equal to C1, C2, Cn, then Fp is just the summation of Ci's. Then define a map T from Cn to C square such that Tp is Fp. So where this Fp lies? Fp is inside uh, C, right? Because what is this Fp? This is just the summation of the complex numbers. Each term of this P is a complex number, right? It's a n tuple in C, element of Cn. That's what it means. So if you are taking a summation of n many complex number, it will going to lie inside C. So C square is uh, uh, having a two tuple elements here are two tuples in C, right? So what is this fp 2 comma 3 means? You just multiply it inside fp 2 comma fp 3, right? It's just a two tuple multiplied by a field element. Okay, so then you have to see that the map T is a C linear map. Okay, so let's check its linearity. A part. Let P comma Q belongs to C, then T of P plus Q is F P plus Q 2 comma 3. Now FP is linear. FP is what? FP plus Q will be so C and it should be CM. Yes, because it's from Cn to C square, right? It will be from Cn. So maybe I think I don't need that, but still, just to make the things more clear, I will write it. So be such that P is some P1, P2, Pn, and Q is some say Q1, Q2, Qn. Then uh, P of P plus Q is F of P plus Q 2 comma 3, and F of P plus Q is what? This is just F of P plus Q is uh, Fp plus Fq, right? Because F of P plus Q is what? P1 plus Q1. Should I write that also? I don't think that it's needed, but P plus F of P plus Q is what? This is summation of F, summation of I
Mission CI, sir.
Ci's, and Ci's are the coordinates of P plus Q, right? So
Yes.
uh, it's already clear, but let me just. So what are the coordinates of P plus Q? It is P1 plus Q1,
The linear product.
P2 plus
And
Q2, Pn plus Qn.
sir, C, can we take C1 and D1 like that?
You can take, that's your choice. It won't affect. It just means ki, if P is an n tuple, you take the summation of all n coordinates. So your n tuple is P1 plus Q1, P2, Q2, and so on. So f of this will be summation of
Okay.
Pi plus Qi. I equal to 1 to n 2 comma 3. Now this summation you can break into two parts: summation of I equal to 1 pi plus summation of I equal to 1 to n qi, right? And what is this? The first part is f of p, the second part is f of q, right? And then it also splits. This is a complex number, this is a complex number multiplied with a 2 tuple. It also splits, right? This is fp 2 comma 3 plus fq 2 comma 3, and fp 2 comma 3 is t p, and this is t q. So this is linear, right? The additive property is satisfied, and you can check that the other part is also there. Uh, that also t of alpha times p equal to alpha times t of p for all alpha belongs to C. That you can check easily, because you just need to use that t of alpha p is f of alpha p, and if what is alpha p, it will be just multiplying alpha to each coordinates and then taking its sum. So summation will be alpha times ci's, and then alpha you can take out, so it will be alpha times summation of ci's, and which will be just alpha times fp. Okay, so just this thing you need to do, and that implies t is C linear. Okay, so yeah, now I think we can move to the next part. So second one says dimension of home cn c square is 2n. So now this is coming from the third part, right? We have v star w, sorry, tensor w over any field is isomorphic to home of v comma w, right? So uh, this implies cn star tensor c over c square is isomorphic to home of cn c square, right? And thus its dimension is, which implies uh, dimension of home cn c square is what? Is equal to the dimension of, so if they are isomorphic, their dimension is also same, right? Home cn c square has same dimension as uh, c and star tensor c square. And what is its dimension? This is equal to uh, the dimension of cn star times dimension of c square, and the dimension of cn star is same as the dimension of cn, which is n times, which is n, and c square has dimension 2, so this is be n times 2, which is 2n. Okay, so b and c is also correct, right? So the fourth part needs again some calculation. Okay, so it uses something that has already been discussed in class. but we missed it because that was a part of a proof. So I will just give some idea, then you can refer to the lecture notes for details. Okay. So, okay. So part D in class, in lecture videos, we have seen that phi from V star tensor W. So V star tensor W is isomorphic to home of V comma W, and the map that makes it isomorphic is this map phi, uh, which maps uh, given by phi of f function. So f is a linear function from V to f. F tensor W, small w, is T of some f tensor small w such that, so T of f tensor W is an element of uh, home V comma W. So it will map an element of V to W. So such that T of f tensor W over V is nothing but FV W. So FV, this is a map from V to F, right? So belongs to V star. So this is inside F. This belongs to V star, right? And this is inside W. So this will be inside W. So there is no issue. Okay. So this map given by this is an isomorphism that is being seen in the class. So here what you have T, image of T is F tensor 2 comma 3. Okay. So T of, this means simply T of uh, P. This implies T of P is, so what uh, what should do? So T is a map in Cn star tensor C square, right? So from here we are supposed to map it to F, where T will be mapped. Phi of, say, T will be nothing but T of, so I should have used some other notation. I think here maybe some psi I will use. Psi of this is this. So phi of T is some psi of T such that, oh, maybe yeah, inverse thing. I think we need the inverse thing. Okay, sorry for it. So see, since T of P is FP, FP 2 comma 3, right? T of PV, T of P is FP 2 comma 3. So you compare it with this. What will you get? Here V is equal to P and W is equal to 2 comma 3, right? So this implies T is nothing but F tensor W, which is F tensor 2 comma 3, right? This is what we have done, right? F tensor W is mapped to FP W. So if something is FP comma FP 2 comma 3, then this is just the map is F tensor W, the pre-image is F tensor W, and then it is just F tensor 2 comma 3. Okay, so uh, there is some confusion. Yeah, so this will be under the inverse image. Phi inverse of T is, because this is T. This is after mapping it under phi, you get it in the form of FVW. So if you take the inverse image, it will be F tensor W, right? And thus uh, phi inverse of T will be F tensor W. So the image of T is just F tensor W. They are not saying under which map phi inverse. They are just saying image of T in Cn star C square is this. So Cn star C square is this side, right? V is Cn and W is C square. So the map will be home V comma W to Cn star C square. That is phi inverse. So we are given an element of home V comma W. We have to see its image under V and V star tensor W. So that is phi inverse. So T is mapped under phi inverse to F tensor W. That is F tensor 2 comma 3. Okay. Okay. So that's it. We can then move to the next question, I guess. Fourth question. So it says that A and B are two matrices over C. The maps T from CM to CM tensors CN to CN tensor CM given by T of X tensor Y is AX tensor BY. Choose all the correct options. So clearly it's a C linear map. So this is wrong, this is right. We can simply see that T of Cx tensor Y, let some C belongs to complex number, that Cx tensor Y. So A is an M cross N matrix, B is an M cross N matrix, and you are mapping element X tensor Y. X is inside Cm and M tuple, and you can see it as a Cm, okay, and you can see as a take it as a M cross 1 column. Okay, then only you can multiply it with, right? So AX means axis must be having the number of rows to be equal to the number of columns in A, that is M. So you have to see it as a M cross N, M cross 1 column to make the definition correct, right? So column. So now C belongs to the complex number, then Cx tensor Y will be mapped to A times Cx tensor By. So C is just a scalar multiplied to the column. So you can take this scalar out and you can write it simply Ax tensor by, right? And that is same as saying C multiplied the entire thing ax tensor by, and thus it is nothing but C of t x tensor y. So it's linear. Uh, with respect to addition also you can see there would be no issue. Now if m equal to n, then one has to see that it's a isomorphism or not. So for that, what you do for C, take A to be a zero matrix. Then T of x tensor y is 0 times x tensor by. Zero matrix multiplied to a column will give you a zero column tensor with by, and zero tensor with something is what? This will be zero, right? So this implies T is identically zero, which implies T is not an isomorphism. In fact, you can take any non-invertible matrix, and for which you can see that it won't be an isomorphism. I took the uh, uh, simplest example when T is a zero matrix, but you can take any non-invertible matrix. Okay, so this is correct. Then this is of course correct, since dimension of Cm tensor C, Cn is same as dimension of Cn times dimension of Cn, that is Mn, and finite dimensional vector spaces of the same dimension are isomorphic, so they are also isomorphic. Okay, so also quickly paste the next question. We are already running out of time. So it says let M be RS bimodule and N be a ST bimodule. Choose all the correct answers. So then this will be absorbed, right? This S will be absorbed, and S tensor S will be an RT module, right? So simply the last one is correct. There is nothing to be checked. We've already seen this. Okay, so this is the simplest question. Just the definition one has to use. Now I will copy the last, copy the sixth question. So it says that I be an ideal of a commutative ring R and M be an R module. Then all then choose all correct options. So first of all, we will see that Ra tensor M. Then these two options will be handled, and then this two can be handled simultaneously. So R by I is clearly a R by I module, and then because R is always an R module, right? And M is an R module, so you can define a R by I module structure over M by just, so R by I the structure is just a quotient of R, right? So using the structure of R, you can define it R by R module structure over M. So both of them are R by R module structure. So R by I, and in fact, I don't think you need this. because one side is a R by I module, so the tensor will also be R by module. If an element of multiplication will be done in just one side, and the second side will be kept as it is. Okay, so just one side multiplication is enough for defining a module structure. So R by I is an R by I module. So R by I tensor M is will also be an R by I module, and then it's saying okay, uh, then by the natural projection. So we saw the restriction of scalars, right? So by the natural map from R to Ri, the homomorphism map. So R by I module is structure is there. So we can give an R module structure. We can consider R by I as R module. Okay. Then what to do? One has to consider the map F from M to R by I tensor M defined as Fm to be one tensor M. Okay, this part is kept or I here, right? Which is zero here. One bar one should consider. One bar tensor M. Uh, then F is R linear and surjective. Okay, that you can see easily why it is surjective. Also, the kernel uh, will contain all elements from IM. So this we have already done in one of the lecture, one of the assignment solution. This kind of thing that IM is contained in kernel F. Thus, we have a thus it induces a surjective R linear map. Just to quotient the domain with whatever was contained in the kernel. So F delta from M modulo IM to R by I tensor R. Okay, so this is a surjective R linear map. Now one has to consider another map. Consider, let's consider it. Okay. So here also we consider uh, a map from M to R by I tensor R. Here what we will do, we will consider a map G from R by I cross M modulo IM, then such that G of R bar comma M is just RM modulo IM. So here G will become a, then G is a well defined, then G is well defined and R balanced. So by the universal property, it will induce a an R linear map. Then there exists a R linear map G delta such that G delta is from the tensor product. Here we are having from the Cartesian product, where it will be the from the tensor product to MIM such that G tensor such that G delta of R tensor R uh, bar tensor M will be just Rm mod M. This is by the universal property of tensor product. So one just need to check that F bar and G bar are inverses of each other. Then we are okay. So this means A is correct and B is not correct. For C, what is needed? MIM is a R module, and the tensor is also we are taking over R. R tensor MIM over R is again the same thing, right? So C will be correct and thus D will not be correct. So that's it. We have done 6 questions. I think I can give some hint for 7 and 8. Uh, so let me just copy paste them, and then I will just give a hint in the next 2 minutes and then stop. So M and P be finite dimensional vector spaces. Then one has to show that M tensor NP is isomorphic to M comma N tensor P, right? So uh, yeah, so this is uh, isomorphic to home N comma P, right? So we will show that home M tensor N comma P is isomorphic to home M comma home and P. So you just define, let's say I give it some name because it's very difficult to write it again and again. A, and then this thing I will say B. Then you define psi from A to B such that, so here it has map from M tensor N to P. So this any map will be mapped uh, uh, to a map from M to home and P. So phi F M should be inside home of NP, right? Because home this is mapping to the an element of this, which means it should be a homomorphism from M to home and P. So it should map each element of M to a homomorphism from N to P. So phi F of M is an element of uh, home and P. So thus it will be a map from N to P such that psi F M uh, N is f of M tensor N, right? M tensor N is an element of capital M tensor N, and F was mapping all elements of M tensor N to P because F is an element of home M tensor N to P, right? So this is a well-defined map, right? So this is inside P. This is a well-defined map, and uh, let H be any map inside A such that for any G belongs to B, uh, define a map H from M cross N to uh, yes, such that so let H belongs to A, and for any G belongs to B, you define a map H from M cross N to P such that H of M comma N is nothing but GM comma N. Then your uh, so what is happening here? So your H is in, something inside A, which means it's a map from uh, okay, don't need that. Simply you can write for any G belongs to B, define a map as M cross N to P such that Mn will be equal to Gm of N. So G is inside P means G is mapping each element of M to an element of home and P. So Gm is an element is a map from N to P. We are defining as just to N evaluated over this map, right? So this will be inside P. Then H is a H is bilinear, and thus by universal property, there exists linear map H tilde from M tensor N to P. Okay, so we will define the uh, map phi from psi from B to A such that for any G, phi of G is just this H tilde. Maybe we can say H tilde of G because it is depending on G anyway. So H of G I can write. Okay. So then H of G is bilinear and this. Okay. So uh, yes. So one has to check that the psi and phi are inverse of each other. So they are so A and B are isomorphic. Okay, which means these two are isomorphic and that this is true. And I will just say one line for last question and then stop. So let me just analyze it a bit. Says that Z mod with the category of Z modules, R mod with the category of R modules. Let F be a map mapping an element of Z mod to R mod such that an Z module is mapped to R tensor M. So this is an R module, and any map F from M to N, a Z linear map is mapped to map from Fm to Fn in this following way. So this is mapping an Z module to an R module and the Z linear map to an R linear map. So one has to check that it's a functor or not. So it will be a functor. You should verify the properties of a functor, but you can see the object are and map wise it is well defined. A Z module is mapped to an R module, and the Z linear map between two Z module is mapped to a F linear map to between two R modules. Okay, you just need to see the other properties of that identity is mapping to identity and it is compatible with the composition. Uh, these two properties you have to verify. Also, you have to see that this is an R module and this map is a R linear. Okay, so yeah, I will stop here. If you have any doubt, then you can ask. Okay, so there is no doubt. Then we will meet tomorrow from 6 to 7, and I will tell you something about the assignment number 11. So that tomorrow is a 1 hour class. So I won't be describing much theory. Uh, if I would think that the theory has to be defined, then I will give hints to the questions, not complete solution I will give. So we have to manage it at some place. So either the theory wise or the solution wise. So I will see accordingly which one is better. And yeah, assignment 12 will be you can take it as an exercise, because I can't solve it tomorrow, because assignment 12's last date is 17 April, which is tomorrow. So I can't solve it tomorrow. So you can take it as an exercise. Assignment number 11 we will see. Okay. Uh, okay then.
Okay, sir.
I will stop here. Thank you.